calculating vectors. Hopefully you've taken a look at one of the previous presentations on what vectors and phasors are. In this presentation, we're going to be looking at calculating vectors with an extremely expensive software that allows us to see 3D representation of digits or fingers that look real. I'm going to try them out right now. Holy smokes, look at that. It even looks as though there's a shadow there. They look so incredibly realistic. I am happy. Okay, so let's take a look at calculating vectors. How is this done? First thing we want to realize is that in the electrical world, we refer to vectors as phasors. A vector is something that indicates direction and magnitude. In electrical, we call these phasors. So it's just a different word for the same thing. Phasors are going to be represented in either a closed or an open arrow, and that's going to be dependent if they're current phasors or voltage phasors. We will not have impedance or power represented with phasors. All right, so what is that going to look like? Well, a phasor is always on a phasor diagram, which is also known as a Cartesian plane. There's always a reference line, and the reference line is always something, some property of the circuit that is common to all the other measurements. So in a series circuit, the reference phasor would be the total source current. In a parallel circuit, the reference phasor would be the total source voltage. We notice that the angle starts at 0 here, 90, 180, 270, and returns back here to 360 degrees, which means that if you wanted to consider rotation or passage of time, it is always in this direction. All right, well, let's get into some calculating. That's what we're here for. Everyone's on the edge of their seat. Magnitude and degrees. There are two phasors. Looks like we've got a 8 volt at 0 degrees and 15 volt at 47 degrees. And what we're going to do is add these two items together. Why on earth would I want to add these two phasors together? That is a fantastic question. And so let's take a look at where these values would have been measured in a real electrical circuit. Ah, there we go. That looks familiar. This is a series circuit. In a series circuit, we have a source and two voltages. Now, I don't know what types of devices these are or what they are really, but I've just labeled them as V1 and V2. And in level 1, we know that Kirchhoff's voltage law would have been utilized in order to determine what the source voltage was. V1 plus V2, the two voltage drops, should be equivalent to the source voltage. Now, in a alternating current circuit where there is a displacement of time between two or more phasors, that will have an effect on how they must be added. You must take into account that phase shift between the two voltages. Now, how is that going to be done? Great question. Let's take a look. There's two different methods. First method is more of a longhand method, but it's one that's easily done, does not take a crazy amount of time, and will transfer to third level as well, and is not dependent on the type of calculator you have. The second method is a little bit quicker, however, you need to have the correct type of calculator, and I'm only going to be showing you the process for the Sharp calculator, which is the one that is identified for use with the apprenticeship training model. So let's first start with an HV table. All right, HV tables utilize a little bit of trig background. So here is the process or the rationale behind what we're doing with the HV table. The first thing we want to realize here is that every phasor has a vertical and a horizontal component. So 15 volts at 47 degrees, and they make up a triangle, right? Hypotenuse is the magnitude, and there's my angle, which would be 47 degrees. Now, if I wanted to work out the vertical component and the adjacent component, then I have to use some of my basic trigonometry. And so the first thing that we're going to do here is we're going to be taking a look at how we use our trig to calculate the vertical component. And the vertical component is going to be using this, sine of the angle. Sine of the angle is equal to opposite times hypotenuse. Now, I don't need to know what sine of the angle is. In fact, I already know what the angle is, and I already know what hypotenuse is. Therefore, I want to calculate the opposite. And so what we do is we manipulate that equation, and in manipulating it, what we get is that missing vertical component of our phasor. Second item, let's look at the horizontal. The horizontal is going to use cos of the angle. And again, I already know what the angle is, and I already know what hypotenuse is. I just want to calculate the adjacent side. And so we manipulate it once more, and we get this, the horizontal component. So how is that then going to be used in the complete sequence? Like, what are we going to do with this? Well, however many phasors I want to add together, I need to know all of their verticals and all of their adjacents. And then it becomes a simple process of adding all the horizontals and adding all the verticals. So let's go back to our example. Our example, we had a 8-volt phasor at 0 degrees and a 15-volt phasor at 47 degrees. And so what I've done is I've taken the 8 volts times sine of the angle equals 0. That's 0 vertical. 8 volts times cos of the angle is 8. There's 8, my horizontal. I did the exact same procedure on the second phasor down here. 15 volts times sine 47 gave me the total vertical, 10.97 over here. And then 15 times cos 47 gave me 10.22, which was the horizontal. At this point, all we do is we add these values together. So this and this gives me 10.97. 8 and 10.22 gives me 18.22. This is the HV table. It's a very simple process. Ooh, there we go for effect. A simple process that allows you to work out what the combined vertical and horizontal components are of two phasors to be added together. But that's not the whole story, is it? Because this is only the vertical and that's the horizontal. We really don't care about those, honestly. We want to know what the actual values are. And in doing that, what we're going to have to do is, again, apply a little bit of trig and a little bit of our Pythagoras theory. So here we are. We've calculated these values, and we've got 18.22 and 10.97. And I want to know what is V total and what is the angle. So let's deal with each of these one at a time. So first thing, let's work out what the total hypotenuse is. So we're just using Pythagoras, which means 18.22 and 10.97. I have a total voltage of 21.26. Fantastic. Now, what about the angle? You have a number of different choices here, but I'm going to say use this one that I'm going to show you. It's fairly important, and the reason is how it's referenced from 0. We're always going to use tan of the angle. So tan of the angle is equal to opposite over adjacent, but I don't want to know what tan of the angle is. I just want to know what the angle is. And so what we're going to do is we're going to apply the opposite of tan. And that's tan to the -1 or inverse tan. And the way that you get this on your calculator is you press second function and then the tan button. In doing that, 10.97 divided by 18.22, and then inverse tan, we get 31.05 degrees. 31.05 degrees. Now this degrees is referenced from 0. So when we plot this, 31.05 degrees is referenced from 0. Depending on the vectors or the phasors you're adding together, this angle might come out negative. So it's important to realize that it is referenced from the 0 mark on your phasor diagram. All right, so here they are, all three of them now plotted, and we can see there's V1, 5 volts at 0 degrees. That's V2, 15 volts at 47 degrees, and V total, which is longer, and it's 21.26 volts at 31.05 degrees. So when we're adding phasors together, typically the resultant phasor is going to be somewhere in between the two phasors that were added. All right, so we've looked at the longhand method. It's pretty straightforward. You simply need to keep track of all of your numbers. The main problem with the HV table is that people will inadvertently write down the wrong numbers because there's a lot of numbers you're writing down, right? There's all the horizontal, all the vertical, you're working out the hypotenuse, and then you're also working out the angle. Mode 3 has less numbers that you're writing down. However, people at times will screw this one up because we're just not familiar with using different modes on the calculator, and we don't second guess anything that comes out of a calculator. So if you put in the wrong numbers, you're getting the wrong answer. So let's take a look at the process involved with mode 3. Mode 3 is going to be used on calculators that are sharp. So mode 3 is for a sharp calculator, and it's not every calculator that's going to be able to accomplish this. Now I've got an older calculator that I can use this with. This is a Sharp EL520W. Really the 520W or 520 is what's of significance here. This calculator will allow me to shift to different modes. So let's take a look. What is the process? Well, it's going to be a number of steps. You have to change your calculator's mode, and then we have different buttons to enter depending on what we want to signify, either an angle or a magnitude. So, step 1. This is setting your calculator in a manner that allows for phasors to be entered. So you're going to press mode, then the number 3, which in brackets should say DEG, second function button, and then the number 8, which has a line, an R, and then this. What we're doing now is we are indicating on the calculator that we are set up to work with phasors. And now this should be displayed on your calculator in the upper left corner of the screen. At this point, you're going to enter in the phasor magnitude. And so if we wanted to, we could enter in the phasor magnitude of our first phasor, which was, what do we have? 8 volts. So we can enter the number 8. We're then going to have to press DMS. And what the DMS does is it allows us to now enter an angle. Because remember, we had 8 volts at 0 degrees. So now we enter the phasor degrees. So it should have like a little angle looking thing on the display, and I'm going to enter in 0. I want to enter in more phasors now. So what I'm going to do is I'm going to enter in the same process that we did before. So what we have is enter phasor magnitude, DMS, enter phasor degrees. So I have 8 volts, angle 0 degrees. I'm now going to enter in the next one. I got to have 12, what was it, 12 volts. And this 12 volts, or no, sorry, 15. It was 15 volts, my apologies. 15 volts at 47 degrees. So I enter in 15 DMS, which gives me the angle thing, and then I enter in 47. At this point, I'm now going to press the equals button because I want to get the sum of these two values. So once I press this, what it's going to show me is the total magnitude of our hypotenuse. So 15 and 47. So if I were to do this on my calculator here, I have mode 3, second function 8. So I have 8 DMS 0 plus 15 DMS 47 degrees equals 21.27 volts. So that is the total magnitude or hypotenuse. Now, if we want to work out the angle, because that's only half of the problem, right? Let's now work out the angle. The angle, we have to enter in this second function, exp. And again, this is the degrees referenced, well, you can barely see it there, from 0. So, second function, exp. On my calculator, it's right here. So exp. And immediately, it shows me that angle symbol, and it says 31 degrees. So there's two different methods for us to add vectors or phasors. You have the HV table, and you also have the mode 3 process. Depends which one you want to use. It does not matter which you choose. For any examinations or for any sort of question related to adding vectors, you could do either one. Make sure that you follow through with whatever method you choose.